Okay, so let me start by thanking the organizers. I see Professor Pinaki here and Professor Purushottam. So for organizing this fantastic conference and for inviting me to give a talk, even though I don't really work on fractures, as you can see. Just like my name, we were just making fun of my surname. I also noticed that the title of my talk is quite a horrible mouthful. So I shall, where is I don't have my specs, so I can't see anything today. Where is the light? Ah, okay, this one. Okay, thank you. So that's a really horrible title of my talk, but I'll just admit that all I mean here is that how do clay gels collapse? And just to put it in context, I mean, why on earth are we interested in clay gels collapsing? And the reason behind that is you've heard of the Uttarakhand problems, perhaps, you know. So, I mean, deposition of silt is a problem that, we'd all like to have a handle on. And what does silt really comprise? Well, a few things like, clay, water, salt, some organic matter, fine sand. Now, so we make, basically what we've tried to do here is we've tried to make model soils in the laboratory. And of course, we've only put clay, water, and salt. We don't have any organic matter, fine sands here. However, as I'll try to convince you during the rest of the talk, that this whole business of collapse of clay gels, this is controlled by an osmotic pressure-driven aging phenomenon, which in turn is controlled by interparticle, inter-clay platelet interactions, okay? So it's a completely electrostatics driven process, and we do not suspect that, adding or taking away, uncharged moieties is really going to make a big difference to what I'm about to tell you today. I will also have to admit that, because this is an experiment that is done in a laboratory, the compositions of the, clays and waters is not exactly what you'd expect, in real soil. But however, again, even though absolute magnitudes might change, we do not believe that the trends will really change in real soil. Okay, and so this was what I'm going to tell you about today is part of the PhD thesis of my ex-PhD student, Shamim Ali. So Shamim got his degree late last year actually, and is now a postdoc at the National Institute of Standards and Technology, Gaithersburg, Maryland. Okay, so this is what a clay particle looks like. So I know many of you work on clay and many of you have heard lots of Laponite talks, but I'm going to go through this anyways. So a clay particle, it's an inorganic macromolecule and it is shaped as a platelet. Now, it has a layered structure. So basically, like I told you, it's an inorganic molecule. It has tetrahedrally coordinated silica layers that sandwich an octahedrally coordinated alumina layer, as a result of which the thickness of a clay platelet is constant, no matter where you procure it from. It's always 1 nanometer. It is this diameter that varies. So the diameter of clay particles, of course, it varies depending on where you procure it from. So many of you work on Laponite. Now Laponite, which is a very famous clay, okay, so that is basically a kind of a designer clay because they prepare it in a way that it is highly monodispersed. All the particle diameters are the same. They are about 30 nanometers or so. Now we will be working with real clays as in bentonite clays, also called Montmorillonite clays, depending on whether you're French or American, also called Wyoming clays. And these are basically clays with a very large distribution of diameters. And I've already told you that you have these silica layers that sandwich an alumina layer. Now, there is some amount of isomorphic substitution of these aluminum groups by lithium and magnesium, which gives rise to negative charges on these flat basal surfaces. Now, the edges, well, they have very different kinds of charge configurations. So they, because of the edge groups, that, if you have say some amount of hydrogen ions in your solution, which you almost always do, the sides get protonated, okay, and they become positively charged. And the strength of these positive charges depends on the pH of the suspension. So the lower the pH, that is more acidic the medium, the more positive the edges become. And as you increase the pH, you find that the isoelectric point is at around a pH of 11, which is when the whole particle becomes negatively charged. Unlike the clay particles, the laponite clay particles, these designer particles that I told you about, which are rigid because of their small diameters, our real clay systems are, not only are the particles rather irregular in shape as well as in size, but because of their sometimes rather long sizes, they are also very flexible. So I'll just show you what these particles look like. So what I have here, I'm sorry, I mean this is not the clearest picture that I could have shown you, but this is us. This is an STM of, this is an AFM, I'm so sorry, of clay particles, and you can see here, so these little white things that you see here, these are the clay particles, and you can see that they are very flexible. They're also rather irregularly sized. So we've taken pictures such as these, and we've calculated a histogram of the number of, you know, the probability of a particular size versus the size of the particle, and we see that the peak lies somewhere around 425 nanometers. Okay, so that is basically the average size of a clay platelet, the kind that we are using here. You also have clay platelets that are as small as say 50 nanometers or as big as 3 microns. Okay, and as you can see, the distribution of sizes is rather wide. Okay, so here of course you see a clay platelet that exists as one single singlet unit, but in real life that is not what happens. We were just talking about this. So clay exists in tactoids, okay, in stacks. So in one-dimensional stacks where they are basically stacked one above the other. And these stacks, okay, so basically the clay platelets in these stacks, they interact through a van der Waals interaction, and there are some sodium ions in the interlayer galleries that basically neutralize the particle, because remember they are a little negatively charged. Okay, so what happens when you put a laponite particle in water? When you put a laponite or any clay particle in water, it releases sodium ions. Okay, and this little egg that you see around our particle, so by the way, the reds here, the red, you know, the red circles that you see here, this is a cartoon for basically it signifies negative charges, and the edges, the black edges are the positive charges, and this blue egg that you see here, these are the diffuse sodium ions that surround the particle when you drop the particle in solution. Okay, so this is a Debye layer, and for those of you who are interested, or who study the DLVO theory for colloidal interactions, you know that the Debye screening length, sometimes designated as lambda, goes as 1 over root of the ionic concentration in solution. So as you can see, if you add or subtract the amount of ions in your suspension, this layer can shrink or expand. Okay, so, and obviously if you have more than one particle in water, by changing the amount of ions in the medium, you can actually induce different kinds of, different degrees of interparticle screened electrostatic interactions.
So if you have these two, suppose you have two such platelets, then are you saying that the electrostatic interaction between this is like it has a prolate?
No, I'm not saying anything like that, you know. It's a very complicated material. So, I mean, this is just a cartoon. So, all I'm saying is this is a particle with a Debye layer around it. It is very anisotropic, and that's the...
Depending on whether you consider electrostatic or unsphere, anisotropy is different?
Well, I mean, so we are going to be looking at rather concentrated suspensions where probably the Debye layers are, So yeah, there is, you know, it is not such a lovely egg as in here. It could be, you know, compressed and deformed and so on and so forth. So if you change the ionic concentration in suspension as well as the concentration of these laponite or these clay particles, you can basically, you can engineer, or you see a sequence of phases because of modification of interparticle interactions. And there are many different phase diagrams that are in the, in the literature, but I will actually come up with one of the oldest phase diagrams that was suggested many years ago, but then which is, in principle, this is okay, though, finer details have changed. So if this is the amount of salt in your medium and this is the volume fraction of the clay, let's look at the slightly higher volume fractions. So at the lowest salt concentrations, you form a repulsive glass, like a Wigner glass. So here's a cartoon of that phase. So these little cigarettes that you see here, these are our clay platelets, and the eggs around them are the debye layers. And here, this is a repulsive glass. As you can see, the particles are basically trying to avoid each other. They are confined by the boundaries of the system. They do not really, there are no attractive bonds between the particles, as a result of which they are completely randomly oriented. If you increase so over here, if you increase the salt concentration a little bit, your debye layer shrinks. So you can see the egg shapes have become more like, circles. And as a result of which, remember, the edges were positively charged and the faces were negatively charged. So you end up with these edge to face kind of interactions. Okay, so you begin to form these attractive bonds, and you end up with structures such as these, and this is what we call an attractive glass because it's not quite a gel. Now if you increase the salt concentration even more, you end up with a network structure as this. As you can see here, the debye layer has almost completely shrunk because you've added a lot of salt here, and you end up, so you have these really strong attractive bonds between the edges and the faces of the particles that form, and they form into a percolating network structure which is held up by the walls of the container. Okay? And if you increase the amount of salt over here, then the gel just falls apart. Basically, you have absolutely no electrostatic repulsion anymore if the amount of salt in the medium is too much. The particles start aggregating. These are called flocks. So they basically aggregate because of van der Waals interaction. Once the effective size of the particle becomes very large, it becomes very heavy, and it just sediments out of the suspension. Okay? So flocks will sediment out of the suspension, and I am a rheologist by training, and all this sequence of phases is very interesting to me because they all exhibit viscoelasticity. Okay, but we are not going to be talking about all these phases today. I shall concentrate on the gel phase. Okay? So this the structure where you had that percolating network structure. Now we go back to this business of tactoids, that is, clays, real clays especially, they don't quite exist as a single particle, but as stacks, as one-dimensional stacks, which, people in the clay business call tactoids. So what are these? What does it really look like? So this is what dry clay tactoids look like. They are little lumps. And so these are aggregated particle stacks, if you will. When you can disperse them into single, single one-dimensional stacks of particles. And I don't know how many of you have a pet cat and you have to use kitty litter at home, but bentonite is basically this, the so-called scoopable, clumpable kitty litter, okay? So what happens is when some water falls into this bentonite, it swells, as you'll just see, and that basically traps the moisture, okay? And that's why you can, it forms these nice hard clumps that you can scoop out. But anyway, we are not going to talk about kitty litter anymore. But then this is, so what happens when you put water in these stacks? The stacks swell. And why do they swell? Because remember I told you that in the interlayer galleries between these individual particles, there were some sodium ions. So when you put this in water, the sodium ions get hydrated. Okay, there's a difference in the osmotic pressure in the interlayer spaces and the bulk solution outside. Okay, and basically this osmotic pressure difference has to be equilibrated. So the sodium ions want to come out of the interlayer gallery. In doing so, it pushes the platelets apart. Okay, so there's a swelling that happens, and eventually when the van der Waals interaction between the consecutive platelets is exceeded by the screen Coulombic repulsion, then the platelets start peeling off one by one. This is an exfoliation process, okay? So basically you put water, you wait for a long time. If the concentration of the clay in water is sufficiently dilute, with time you will form single platelets in water, okay? And like I told you, a single platelet looks like this, negative faces and positive sides. Okay, so this is basically how clay tactoids exfoliate. And so clay suspensions age. Okay, if you make a new clay suspension, so clay is like a powder, you put it in water. Initially it just looks like it's only a little more viscous than water. You come back after some time, you see that it has spontaneously, something has happened which makes it difficult to flow. If you come back tomorrow, it has become a soft solid. Okay, so you can actually take that same vial and turn it over, and the clay can actually support its own weight. So what is going on? And I do not have time to discuss what is really happening in detail, because it's really outside the purview of this talk. But this happens because of a gradual evolution of the electrostatic interaction that happens, okay, the interparticle electrostatic interaction that happens because of two factors. One is because of the crystalline and then the osmotic swelling of these tactoids, and the other is because of the release of the sodium ions, the formation of D bilayers, and the interaction between these D bilayers, okay? And yeah, so no more about that, but I do have proof that yes, if you wait long enough, there is an increase in the concentration of sodium ions in solution, and this is a measurement that we made using a sodium ion selective electrode. So basically the concentration of sodium ions do spontaneously go up in solution. Basically what that means is there is a spontaneous evolution of the electrostatic interaction that is giving rise to much of what I'm about to tell you about. Okay, so I promised that I'll talk about clay gels, that is clay particles in salty suspensions. But then first let us try to understand what happens without salt, okay? And there's some amount of problem working with this bentonite material, because it's a rather hard material to work with, because at the concentrations at which we are working, it looks like mud, okay? It is completely muddy, and we do our size characterization usually using dynamic light scattering. Now dynamic light scattering only works in a single scattering limit. You need the suspension to be completely clear. Okay, and also to get a size estimate out, you need to be able to use Stokes-Einstein, which is not true in this case because you're really looking at a Wigner glass. Okay, so we use sound. So instead of scattering light, we absorb sound. And I will tell you a little bit about the technique that we use. So this is a machine that we custom made in our laboratory. I'm happy to talk to you about it because we are very proud of it. But I'll tell you the results that we got. So we were basically looking at a suspension of clay aging, okay? And we were computing the sizes of these tactoids, the size distribution of these tactoids as the aging happened. So initially I'm just going to draw your attention to two data points. One is at age of 0, that is with a freshly prepared sample, which are identified by these diamonds, and one is a rather old sample that is about 58 hours old. So a lot of exfoliation has already happened. So these are the triangles. Now if we look at the diamonds in this plot, so you can see that this is the particle size distribution. So you have very fat particle size distributions, and this part is hardly visible, but you basically have one distribution, a fat distribution for the lower sizes, and another fat distribution though of a much lower amplitude for the higher sizes, okay? So when you initially make a clay suspension, there's a huge distribution in the sizes. But as you wait longer and longer, the particles, the stacks start breaking up into single particles or, into multiplets, smaller multiplets. So if you look at the sample at 58 hours, which is this, the data that is represented by triangles here, you see a very sharp peak at the lower sizes, which means that many particles have broken up into smaller units, and also there is another peak, but at much lower sizes. Okay, so what this essentially means is that at larger ages, there are a few big aggregates, but most of them have broken down into singlets or multiplets of a small number of particles because of this exfoliation process. Okay, so what happens when you add salt? So what we found was that the way you add salt is also very important. So there are two ways in which you can make a clay gel. One is when you take brine, which is basically salt water, and you put your clay particles and you let them evolve into the gel. Now this gel we find is very different from the gel that you form where you take clay and water and then you put the salt later on, and that is because of the different osmotic pressure conditions in these two samples. So the gel in which we put the clay in the brine solution we'll call SBC, which is salt before clay. And what happens there is, remember you already had brine, so you had lots of sodium ions in suspension, in solution when you dispersed your clay particles. So therefore, the osmotic pressure difference between the sodium ions in the interlayer galleries of the clay tactoids and the bulk solution is very low. As a result of this low osmotic pressure difference, there's not a lot of exfoliation that happens, so you end up with very large aggregates of particles. Okay, yes.
You add salt to the clay after it's gelled. Is this dialysis or?
Well, we haven't, many people.
Salt after clay, how do you add the salt?
Yeah, so we just add salt, so we just let it exfoliate for some time, and then you add salt, okay.
Pouring it in?
You just pour it in. You could do dialysis, I know many people do it, and they do it precisely to, make sure that these differences don't happen, but then we wanted to see why these differences happen. Okay, so yes, so after some time we just, was there another question? Okay, no. So we just add the salt, and now remember, some amount of exfoliation has already happened. When you're adding the salt externally later on, the osmotic pressure difference is much larger between the interlayer galleries and the bulk solution, and therefore there is some amount of tactoid exfoliation that proceeds to happen, and you end up with smaller particles and you end up with a gel with better network connectivity, which is more stable than this particular gel. And indeed, these gels, they collapse very quickly. Okay, so I will again show you some of our ultrasound data without really explaining how we got them. But then, so this D1 that you see here is basically an effective spherical diameter of the clay particles whose sizes we've been measuring versus the age of the clay particle. So these black dots that you see here, the black squares, this is for clay particles without any salt at all. You can see that these are these give you the smallest particle sizes. Now if you add the salt a little later, you can see that exfoliation is inhibited because the sizes are bigger, but not very much. But then if you made the suspension in brine solution, the clay suspension, so these are the brown circles, you are going to see that the sizes of the particles are much larger. That is, the tactoids have not exfoliated at all. Okay, and because in the case of the salt before clay suspension, you have much larger particles, they also collapse much faster. Okay, so being rheologists, we love characterizing everything with G primes and G double primes, and that's what we've done here. So here the G prime of course is the elastic modulus, the G double prime is the viscous modulus. We've measured this versus, we've measured these parameters versus angular frequency for both our gels. We've applied a very, very low peak to peak strain amplitude, and this is what we see. So henceforth, by the way, our black symbols is always for the gels in which the salt was added afterwards. The red symbols is for the case where the gel was made by dispersing clay in brine. Okay, and as you can see here, there are certain features that are quite ubiquitous. We'll just look at the low frequency because as far as the viscous modulus at least is concerned, the high frequencies is completely dominated by the viscosity of water. You can see that G double prime goes as omega in this regime. So if you look at the low frequencies, you're going to see that the elastic modulus is pretty much independent of frequency. The viscous modulus is, well, slightly dependent on frequency. And the other thing is that the elastic modulus is way higher than the viscous modulus, and that means that you have a solid-like sample, and as I'm going to show you pictures, these are all gels. Okay. Another thing that you see that, you know, for the less stable samples, that is the samples in which we've made the clay suspension by adding the clay particles to brine, we can't really make our measurements at really low frequencies. Really low frequencies, of course, correspond to really high time scales, and the reason why we can't go to low frequencies is because the gels collapse. So this is our promised custom-made sound setup. So what you see here, this stainless steel thing is a transducer which can send ultrasound bursts, and this is our muddy clay sample. There's another transducer here that can receive the attenuated ultrasound signal. So we can, we use Beer-Lambert's law, we can change the length of this sample, and we can calculate an attenuation coefficient at several different frequencies. We can calculate the velocity of sound as the sound waves propagate through this medium, and by modeling the data appropriately by assuming only viscous loss, we get a size distribution out. If you're interested about it, I'm more than excited to talk about it later. But nevertheless, for the salt before clay suspension and the salt after clay suspensions, these are our attenuation spectra, and you can see very clearly from the size distribution plot that in the case of the suspension where we added the clay to brine solution, our SBC sample, the particle sizes are bigger. Okay. Okay. So Shrikant told you, so obviously we are looking at gel collapse, so you want to see how these two gels collapse. And Shrikant told you yesterday about the dilemma in deciding which is the yield stress, and yes, it is very hard. So we have, well, there are about a dozen different ways of doing it according to the literature, and we chose one that was the most convenient. For this we have to do an oscillatory strain sweep experiments, a little bit like what Shrikant was talking about yesterday. So you keep your sample in, you know, in a cup and bob geometry in this case. You apply oscillatory strains. Okay, so here you keep you strain it at a fixed frequency, but you progressively increase the peak-to-peak strain amplitude. And G prime again is the elastic modulus, G double prime is the viscous modulus, and you see that at the lowest peak-to-peak strains, the viscous and the elastic moduli do not really change. And what that means is that the sample microstructure is not changing here because the strains that you are applying here are really, really small. Now, as you increase the strain by a little bit more, you can see that things are beginning to happen. Okay, the viscous modulus starts going up, and this is because of plastic rearrangements that have now started within the sample as a result of, you know, so basically the breakup of the microstructure has started. So the dissipation increases, the viscous modulus goes up. Simultaneously, the elastic modulus starts going down, and if you increase the strain amplitudes even further, the the sample begins to flow. As you can see at the highest strains over here, the viscous modulus is higher than the elastic modulus, right? So by applying the strain, you've basically converted your viscoelastic solid into a viscoelastic liquid. Okay? What you have achieved is an yielding transition in the material. Now we come back to the question of how we characterize this yielding transition. So there's this very nice paper of, you know, that came out from Dusseldorf, where they managed to separate the elastic part of the stress from the viscous part of the stress. So you basically, you multiply you find the product of the elastic modulus with the peak-to-peak strain, and that you find, you know, these are the pink triangles that you have here, gives you a straight line up to a certain limit, and after that it starts basically diverging from the straight line fit. So the point at which the data, which is the pink triangles here, start peeling off from our straight line fit by about 3% or so, which we have completely arbitrarily we have designated as the yield stress. Now you could pick a quarrel with me regarding the way I have calculated the yield stress, but however you calculate it, even if you use a different protocol, you're going to find that the trends are the same. The absolute magnitudes might just change. Now for our laboratory clays, So we calculated our yield stresses, and for our laboratory clays, we find that when we increase the salt concentration, the yield stress is non-monotonic, okay? So the yield stress increases up to a certain limit, and then it goes down. Now, why is this happening? Because it's always a gel, right? Yes, it is a gel, and I will show you pictures to show you that it is always a gel, but the reason why the rheology changes is because the morphology changes. And how does it change? So there are different ways in which these rather complicated particles can aggregate. At very low salt concentrations, they aggregate like this, like overlapping coins. Okay, so you have these face-face kind of overlapping structures, and I can show you pictures. So this is a scanning electron micrograph taken under cryogenic conditions, where you can actually see that, this is happening, because remember I told you that the size of a platelet is about 425 nanometers. I'm sorry, you cannot see this size bar. It's about 3 microns, so you can see that this is much larger than, it's one micron, much larger than the 425 nanometers, which is the size of a platelet. So basically each branch of a honeycomb, it basically corresponds to many overlapping particles, okay? You can also see holes in these network branches, okay? Now as you increase the salt concentration, you have these configurations that start arising, okay? So basically the positively charged edges that bind with the negatively charged surfaces. And indeed, if you look at this very carefully, you're going to see these T junctions that are starting to form. If you increase the salt concentration even further, I'll just show you my cartoon once, okay? So then the van der Waals interaction starts overcoming any repulsion that might have been there because of screened electrostatic repulsions, and particles start sticking together, they coagulate to form thick branches, okay? And that's exactly what we see in our pictures. So we've quantified all these. I'm not going to show you the data. It came out in this paper last year. But so basically, you have these really fat branches in the gel that form at really high salt concentrations. And as a result of these rather heavy branches, the clay gel collapses. Okay, and by the way, all these structures that I showed you, this is not something that I thought up. All these have been, people have gotten these structures earlier for clay platelets in the presence of salt using Monte Carlo simulations. Okay. So now I will come to our experiment, which is the collapse of clay gels. So this is a really simple tabletop experiment that we did to basically to track the settling interface of a collapsing clay gel. And how did we do it? We of course made our clay suspensions with salt, without salt, as well as salt added in various stages of the sample. So in one case the salt, you added the clay to brine. In the other case you added the salt to clay suspensions at different ages. And so this is our setup, not very clear, so probably it's better to look at the cartoon. So we have an LED source. We have a linear LED source. In front of that, so it's an array of LEDs, red LEDs, 633 nanometers. We have a light shaping diffuser in front. So the light that's coming out on this side is really a homogeneous diffused beam. And you have a sample here. Actually, we do it with many, many samples, as you can see here. But well, for the time being, let's imagine we have just one sample through which our light propagates, and on the other side, we capture the intensity profile that comes out on this side on a CCD camera. Okay, so obviously, if the gel is collapsing, there will be more transmission, there will be more transmitted intensity. So the CCD camera will, near the supernatant, for instance, the CCD camera will record a much higher intensity, but as you go down the sample, especially where you form a sediment, which you do, you're going to hardly have any transmitted intensity. Okay, so we're basically tracking the profile of the sedimenting interface, and we are trying to understand the differences in the different, in the different kinds of clay suspensions that we have made here. What happens without salt? This is our transmitted intensity data versus the height of the cell. H is equal to 0 is the bottom of the cell, and indeed you can see, and this is basically with increasing time. So Ts is basically the time of collapse, okay? So you're just letting it collapse, and at several instances you're looking at the intensity profiles. So at the lowest H's, that is right at the bottom, you can see there's hardly any transmitted intensity, and that is basically because there are sediments that are forming that are not letting any light transmit. And as you go up the vial, you're going to see that the transmitted intensity is going up. And what that means here, if you look at the data, it becomes quite clear that there is no abrupt interface, okay? Whatever is happening, it is happening very gradually. And so the arrows that we have here, these correspond to the heights of the sediment, which you can see the height of the sediment is increasing as you increase the time for which you are allowing your sample to collapse. Now, above the height of the sediment, you can actually fit the intensity transmission data to an exponential function. Okay, the characteristic length that comes out from this exponential fit H0 basically tells you about the intensity gradient across the sample, which also tells you about the concentration gradient. You can see that the H0 is the largest for the sample, which the sample with the longest settling time, and that is because the smaller particles basically they diffuse in the opposite direction. So you have a diffusive flux in the direction opposite to the direction of gravity, and therefore you have a kind of a homogenization that takes place with time. Okay, so that is the data with no salt at all, and as you can see from the picture here, so this is the intensity profile that we've recorded. There is no interface, okay? So, but in a gel, which is like a solid-like medium which collapses, you would expect an interface, and that is indeed what we see when we add some salt. So these are the transmission profiles versus H, and this is with increasing settling time. So this is, so A is when we started the experiment, and these are the black dots that you can hardly see. So initially, which is the black data points here, you see no change in the intensity profile, and that is because the system has not really started to collapse. Now, as the settling time increases, you suddenly see, so this would be this sample, you suddenly see a sudden abrupt jump in intensity. And that is because it has started collapsing, so basically the interface is, as the collapse progresses, you can see that the abrupt change in the intensities is happening at lower and lower H's, okay? And remember, I also told you that how the clay collapses depends on whether you added salt before or after, and that is indeed what we see. When we added the salt before we added the clay, we found that you didn't really have as abrupt an interface as you did in the other condition, but then it looked something like this. Okay, there was a more gradual collapse, but when you added the salt later on, you actually find something rather different, which is that the gel is stable for a much longer time. In this case, it had a quiescent regime of about 9 hours. So you form this completely stable gel for a rather long time duration, which, by the way, you can control by changing the salt concentration as well as the concentration of the clay. And then suddenly, after these 9 hours, after this initial quiescent regime, there's this transient collapse. Okay, there's this transient collapse, and then there's this compaction that happens. Okay, so therefore, when salt was added, does determine gel stability. Okay, now like I told you, you can control this interface collapse by changing the salt concentration, and that is indeed what we see. As the salt concentration increases, your Debye repulsions, your DLVO repulsions go down. The clay particles start aggregating, they become heavier, they're going to collapse earlier. As you can see, the green dots are for the suspensions with the highest amount of salt, and yes, they do collapse much earlier. So basically, the more salt you have in your medium, the more likely is the soil to collapse more. Okay. We've also calculated the velocities of the interfaces. So again, we find that the velocities are higher. The velocity of collapse of the interface is higher when the salt concentration is higher. But the collapse does not really happen very smoothly. So what happens is you have these intermittent events where you have the, the branches that kind of, so you can define, you can think of a local yield stress that is associated with every part of the sample. The moment that local yield stress exceeds, the moment the gravitational stress exceeds that local yield stress, you have local microcollapses. As these local microcollapses happen, parts of the gel can come together, they compact, they kind of stabilize for a little bit of time, and then it collapses again. And therefore, you see this kind of intermittent velocity if you look at the interface very carefully. And now after some time, after a lot of collapse has happened and the gel is already rather compacted, the velocity just goes down because there's no more space to have any more intermittent collapse. Okay, so as you can see at the highest times, settling times, the velocity pretty much goes to 0 and you form a sediment. Okay, so being rheologists, we'll always do rheology. Now doing rheology of a sedimenting suspension is rather hard. So we basically had to make our own geometry and calibrate our rheometer accordingly. But what we've done is we've looked at the rheology of the suspension at a distance in the sample which is slightly above the sediment. Okay, so we've plotted G prime here versus the settling time. And the green data that you see here, this is for the highest salt. The black data is for the lowest salt. And you see that, initially the G prime builds up, the elastic modulus builds up very slowly as the sample begins sedimenting. But then well, I shouldn't say sedimenting, but initially it coarsens and then it starts sedimenting. And when it starts sedimenting, you start seeing these oscillations. So we isolate those points where the oscillations start in the rheology data and compare these with the points at which the basically you got the transient collapse in the interface settling data. So we call that tau d, the collapse time from the interface settling data that we got through light transmission, and the places and the times at which the oscillations showed up in the rheology data, and which we call tau d. Okay, this was tau r, this was tau d, and you see that they are right on top of each other if you plot them together. Okay, so these are the points where the settling has really started. Okay, and so this settling, we can actually, we can explain by looking at pictures of the gel. So what we are trying to say is that as the gel collapse progresses, there is coarsening of the networks, there are some rearrangements that happen, driven by thermal fluctuations, driven by the local gravitational stresses, and the gel becomes more and more porous, which can explain pretty much everything that I've been showing you here. And here are our pictures. So again, these are I'm actually done for once. So these are the pictures of these are the scanning electron micrographs in the cryogenic regime taken of our gels. So these are of two different salt concentrations with increasing age. So basically increasing settling time. So initially for the freshest gels, you're going to see that you have more compact structures, it's these wavy compact structures with short network branches. But as time goes on, the structures coarsen, okay, the particles, they rearrange between themselves and they form larger pores. Okay, so and as the pores become larger and larger, of course, the local yield stress, the gravitational stress will easily exceed the local yield stress, and the system can collapse. Okay, so you see pretty much the same thing for a higher salt concentration. So this is a cartoon that we were asked to make by the referee. So you initially have a gel that looks like this, then you have these network branches that coarsen, and eventually you have, so these network branches flocculate, and eventually because of the sheer weight of the gel, you see this transient collapse. So inter and intra-tactoid interactions and the osmotic pressure differences that leads to exfoliation, these dictate the morphology as well as the stability of these salt-induced clay gels. Now we've recently taken an interest in acid-induced clay gels because acidic soil, for instance, this is very important to understand in the context of agriculture. We also recently found out that there's an anti-cancer drug called doxorubicin, which is basically intercalated between the plates of laponite particles, laponite clay particles, and that are delivered to cancerous tumors. Now, these dissolve only in an acidic medium, and therefore the delivery of this drug only can happen in an acidic medium. So it's also kind of worthwhile to study laponite in an acidic, laponite or any clay in an acidic medium, which we are doing. I'm not going to show you the data today, we are writing it up at the moment, but we find that acid-induced clay gels, we find that in acid-induced clay gels, the changes in structure with age as well as with acid concentration is far more dramatic than what I've shown you here. Okay, so basically all I'm trying to say is if we can somehow control the microstructure of the material, we can control the way it behaves, its dynamical properties. Thank you. We haven't done it. Why do you want to visualize it from the top? To do waves and all that, right? I mean, yeah. I mean, we don't know how to do it because, whatever changes are happening are over very small length scales. The sample size was rather large. So the interface size was about maybe no, I'll tell you. Let me not make guesses, but so yeah. So this was about, the interface was about 9 mm and the sample was about 45 mm. pHs, right. No, it is not. It's actually alkaline. It's alkaline. We are slightly alkaline. So therefore, when you deliver the drugs, you need to deliver it in a condition where there's a, the neighbor has an acidic pH. So basically you deliver well, I mean, I don't know, maybe you just, deliver the drug and inject some acid so that it can actually break up. So this is completely, irrelevant, I mean, to clays, but we have done these, we did make these drug capsules out of triblock copolymers. So these are these self-associating copolymers, right? And you can trap drugs in them. And drugs, of course, are hydrophobic, so they like going and sitting in the hydrophobic centers of these, what are essentially spherical micelles. So if you increase the pH locally, so I had a tennis elbow, for instance, okay? And I was being given drugs that were suitable to my body weight. You just use a part of it and you just excrete the rest. Now these capsules that we made, they were 100 nanometers, so you can deliver them through intravenous injections. But you need to release them, right? You can't just deliver. So then you can actually release them by increasing the local pH, by adding a shot of alkali, for instance. So we were using sodium hydroxide because, we don't know a lot about what doctors do, and I mean, we are working on all these things. So yes, you could do certain things like that. So for superficial injuries, I guess, but perhaps, yeah. One has to talk to a pharmacist or a doctor about it, which we haven't quite done yet. Okay. Yes. See, I can't see anything because I don't have my spectacles. No, I will find it. I'll just take some time. Yeah. I think we go down a lot. This one, right? I will make it bigger. Oops. Ouch. Okay. Yeah, I did from the start. Yes, thank you. So, this one. Huh. So, see what is happening is we are using a cup and bob kind of a geometry. So we have a, so suppose this is my sample. Imagine this is a three-dimensional sample. So you have a sediment up to here. So normally when you do rheology, you need the, so you have a bob, right? The tip of the bob has to touch the bottom of the cell. But we didn't want that because we really wanted to see the changes in the G prime as a result of the settling process. So we made our own geometry and we calibrated the rheometer so that we could actually take the data at distances within the sample that was higher than the sediment distance. So initially you find that, so initially when the settling is happening, as you can see here, there is a gradual change in the elastic modulus, which is because of the compaction of the gel. And after that, so you have this very complex process of exfoliation that is going on, plus, you have aggregation, you have these branches that break and then reform again. So there's a lot of microstructure evolution that's going on at those heights, which is above the sediment height. And that's when you see these oscillations starting to develop. Oscillations in G prime basically indicates a change in the mechanical properties because of the change in the local sample microscopic structure. So this is really not a, like a spatial average or anything, it's just at one place. But then you can do it at several parts of the sample and show that these oscillations will show up because of this, continuous, intermittent structural build-up and break-up process that is happening within your sample. And we find that the times when the oscillations start, that remember I told you that so initially you have a quiescent regime and then you have a sudden collapse. So the time at which the collapse starts, which is what we found through this light transmission experiment, this completely coincides with where the oscillations in the rheology start. Well, here are the frequencies of oscillation. It depends on the microstructure, but it's so difficult to really give one answer to this question because there are many things that are going on. So basically there are two things here. So it's a balance of two stresses. One is a local yield stress, the other is a gravitational stress. So it's a balance between the two. So that changes depend on the local microstructure. So when that changes, when the yield stress becomes, when the gravitational stress becomes higher than the local yield stress, you have a collapse event and then it reforms again and then, it stabilizes and then it basically collapses again, and that's how you get these wild oscillations.
You showed some high resolution images of these this. Can you do that while the thing is collapsing?
No. See, because you need minus 190 degrees in a vacuum condition. So, okay, so there's a thing about, imaging colloidal particles is very hard at room temperature because they're going to diffuse around, they're going to move, you're only going to see a blur, right? So the only way you can do it is if you can suddenly freeze it. You quench it very fast, you freeze it, and then you're just hoping that it freezes in the structure in which it was earlier. But referees will always complain because of course, it's a very violent treatment that you're meting out to your sample.
Is there any data on how the thing changes
In situ, you can't do it in situ because you're doing it in vacuum, and also you can't do it at freezing temperatures because everything will just freeze. So you need the thermal fluctuations, you also need it to freeze. So, well, we've run into trouble because of all this. Exactly, we need computer experiments.